everyone, welcome to my channel Math 6 IIT Academy. Now let us discuss about relations on set. Okay, so before going to define relation, let us come to a point called order pair. So for this I am taking a set, let A be any set and A comma B which is belongs to A, and the order pair is denoted by open interval of A comma B, where A is called first coordinate and B is called second coordinate. Okay, so this is about order pair. Now let us come to the definition of Cartesian product. Okay, so for this I am taking two sets. Let A and B be any two sets, and Cartesian product of the two sets A and B is denoted by A cross B, and which is defined as set of all order pairs. Okay, so that is nothing but A cross B is equals to open interval of A comma B such that A belongs to A and B which is belongs to capital B. This is the Cartesian product. So here first element means first coordinate from the first set and second coordinate from the second set. Okay, so now we'll see some point here. So first, if mod of A means Cartesian means order of A is equals to P and order of B is equals to Q, then order of A cross B is equals to PQ. That means number of elements in A or cardinality of A is equals to P and cardinality of B is equals to Q, then number of elements in A cross B is equals to P into Q. Okay, so here let us see with the example here. So I am taking A is equals to 1 2 and B is equals to 1 2 3. Okay, so now these are the set, and here mod A means number of elements in A is equals to 2 and cardinality of set B is equal to 3. Now first let us define what is A cross B here. So A cross B means set of all order pairs whose first elements are from first set A and second coordinate elements or second elements are from set B. So here 1 comma 1, 1 comma 2, 1 comma 3, next 2 comma 1, 2 comma 2, 2 comma 3. Okay, so this is what our A cross B. Now see here how many elements are there in A cross B. Just count 1 2 3 4 5 6. Okay, so which is same as mod A into mod B, that is equals to 2 into 3. So mod AB or mod A cross B is equals to PQ, and which is equals to mod A into mod B. Okay, suppose here we have defined A cross B. Now if you try to define B cross A in the sense set of all order pairs whose first element from set B, second element from set A. So here set B consisting 1 2 3 elements and set A consisting 1 2 elements. So first set is B here. So elements we have to take from set B and set A now. So 1 comma 1, next 1 comma 2, next 2 comma 1, 2 comma 2, next 3 comma 1 and 3 comma 2. So this is our B cross A. So when you compare A cross B and B cross A, here the elements are not equal. Here 1 comma 1 is there in both the sets, 1 comma 2 is also there, here 2 comma 1 is there, and 2 comma 2 is also there, 3 comma 1 is there in B cross A, but it is not there in A cross B. And 1 comma 3 is there in A cross B, which is not there in B cross A. Similarly, here 2 comma 3 is there in A cross B, but it is not there, and 3 comma 2 is there. So here, with this example, we can clearly say that A cross B is not equals to B cross A. Okay, this is one more point. And now the third point is, if A is empty set and B is empty set, then A cross B is also empty set. So this is one more point we have to remember. Now come to the some theorems on Cartesian product. So A cross B union C is equals to A cross B union A cross C, and A cross B intersection C is equals to A cross B intersection A cross C, and next A cross B minus C is equals to A cross B minus A cross C. Next, here when we have A is subset to B, then for any set C, A cross C is subset to B cross C. And also, if A cross B intersection C cross D is equal to A intersection C cross B intersection D. And one more point we have, that is, if A is subset to B and C is subset to D, then here A cross C is subset to B cross D. And one more point, the last point is, if A is subset to B, then A cross B intersection B cross A is equal to A square. Okay, so these are the some important points here in Cartesian product. Now let us see relation. So to define relation, we must have to take non-empty sets. So here I am considering, let A is not equals to pi, means A is not empty set, non-empty set. Here B is also non-empty set. So let A and B be any non-empty sets, and R be any relation from set A to set B is subset of A cross B. Okay, here relation is nothing but simply it is a subset of the Cartesian product of any two sets. Okay, so that means R is subset to A cross B. Here what is A cross B means? A cross B consisting of all the order pairs whose first element is from first set and second element is from second set. Okay, so this is about the relation. Relation is nothing but simply it is a subset of the Cartesian product. Okay, so now we will see some point here. So take it as a note. And any subset of A cross A is a relation on set A. Any subset of the Cartesian product A cross A is relation on A. And suppose if mod A is equals to P and mod B is equals to Q, means number of elements in A is equals to P and cardinality of B means number of elements again is equals to Q, then already just now we discussed number of elements in A cross B is equals to PQ. Now number of relations from set A to B. Number of relations from set A to B means here it is nothing but subset of A cross B. So subset means there we discussed in sets that if a set contains n number of elements, then it must have 2 power n subsets. So here also we will use the same technique. So number of relations, then number of relations from A to B is 2 power PQ. Okay, so this is one more point. Now come to the types of relations. So first one, empty relation. Okay, if R from A to B is any relation and is said to be empty, relation if R is equals to empty set, means R is empty, then the relation is called empty relation. So here let us see with the example. Okay, so here just take sets first, and I am defining set A like 8, 10 and here 12, and I am taking set B is equals to suppose here 1, 3 and suppose 5. Now here we can define A cross B. Okay, and after that we can define relation R, but directly I am defining what is R here. So I am giving the condition, means relation. So R consisting of order pairs A comma B, whose first coordinate is from A and second coordinate is from B, and also I am giving the condition here, that is A minus B is even. Okay, so now this type of relation I am taking on the two sets A and B. Got it? Now here is it possible, here A comma B means here first element from first set, means that may be 8, 10 or 12. So here when you are selecting 8 and B, second element is from second set, A minus B is even. So here 8 minus 1 is equals to 7, it is not even. 8 minus 3 which is equals to what? Here 5, it is not even. And here 8 minus 5 it is equal to 3, it is not even. Okay, so here we are not getting even number. Similarly you can check with the number 10 and also 12. 10 minus 1 9, here 10 minus 3 7, all these are not even numbers, you are getting odd numbers only. So here none of the number will come, so here R is empty relation. Okay, so this is the first relation. Next, universal relation. Okay, so universal relation, if R from A to B is said to be universal relation if R is equals to A cross B. Okay, so here we will see example. So very simple example I am taking here 1 comma 2 and I am taking B is equals to 2 comma 3. Now if we define R like this, here 1 comma 2 and 1 comma 3, next 2 comma 2 and 2 comma 3, and this is nothing but our A cross B. Okay, so here the relation is equal to A cross B, so the relation A cross B is a universal relation, or R is universal relation on both the sets A and B. Next we have identity relation. So now let R be any relation on set A, means R from A to A is a relation such that if usually what R consisting of set of all order pairs, here first element is from first set and second element is also from second set, but here second element is also second set is also equal to first set A. So A belongs to A, B is also belongs to A, such that A is equals to B, then the relation is called identity relation. This also we can denote like this symbol I. Here we are taking set A, so in suffix you can write A. Identity relation on A means I suffix A, which is equals to A comma A simply. Okay, so here we will take example. I am taking A is equals to 1, 2, 3. Okay, so now we can define. First I will define the Cartesian product, and I will make it is very simple to you by defining the Cartesian product and also relation. Then we'll discuss what is identity relation. Okay, so first I am defining the Cartesian product of A cross A. So here A cross A means here what, how many elements will come in here? 1 comma 1 and 1 comma 2, 1 comma 3, next 2 comma 1, 2 comma 2, 2 comma 3, next 3 comma 1, 3 comma 2 and 3 comma 3. Okay, so now this is our Cartesian product. So now what is the relation? Relation means it is any subset of A cross A. So what type of subset means? Here we have given the condition. So here the condition for identity relation is first coordinate is equal to second coordinate. So then the relation is called identity relation. So here now I will define now. Identity relation means here now first coordinate and equal to second coordinate. So here elements 1 comma 1, 2 comma 2 and 3 comma 3 will come. So identity relation means this one. Okay, so simply first coordinate and second coordinate must be equal in identity relation. Next, inverse relation. Inverse relation. Suppose R be any relation from set A to set B, then inverse relation is denoted by R inverse, and which is defined from set B to set A. That means R inverse which consisting the elements B comma A such that A comma B which is belongs to R means relation R. Okay, so simply here we will interchange the coordinate. Second coordinate will come first and first coordinate will come second in inverse relation. Okay, so suppose here I am taking set 1 comma 2. Next Cartesian product is what? A cross A is equals to 1 comma 1, 1 comma 2, next 2 comma 1, 2 comma 2. So this is the Cartesian product on set A. Next relation means it is any subset. So here subset means you can take 1 element, 2 elements or any number of elements which are present in A cross E. So here simply I am taking here 1 comma 1 and 2 comma 1. Okay. So now R inverse means what? Now here we have to change the second coordinate as first coordinate and first coordinate as second. So first as second means 1 comma 1 and second as first. So here 2 I will write as second coordinate and 1 I will write as first coordinate. So here 1 comma 2 and 1 comma 1 are there in R inverse, and 1 comma 1 and 2 comma 1 is there in R. Okay, so here both are different, not same. This is about inverse relation. Next, now from this point onwards it is very important now. Here reflexive relation. So reflexive relation. So here let R be any relation on set A if every element is related to itself. Simply I am writing A is related to A for all A belongs to set A. Okay, reflexive relation means I am taking R is any relation on set A if every element in set A is related to itself, then the relation is called reflexive relation. Okay, so here we will see one example. Here X divides Y, where X and Y which is belongs to N. Okay, So here x divides y means when you are taking every element in natural number, here x divides x, y divides y, every element is divides itself. So this divides is reflexive relation on natural number system. Okay, so here if you can't understand, I will give one more example. Simply here I am taking 1 comma 2 as set A, and next here and I am writing relation R like this. Here 1 comma 1 and 1 comma 2 and 2 comma 1 and 2 comma 2. Okay, so this is the actually Cartesian product, and that I am taking as relation R1, and here we can define one more relation, that is 1 comma 1 and 2 comma 2, and I will define one more relation also, that is R3, which is like this 1 comma 2 and here simply here 2 comma 1. So we can define the relations like this. So in this R1, R2, R3, which are reflexive relations? So that in the sense every element is related to itself, then only we can call it as reflexive relation. So 1 comma 1 should be there and 2 comma 2 should be there in the relations. So here 1 comma 1 is there and 2 comma 2 is also there. Okay, rest of the elements also there. Of course it is not a problem, because every element is related to itself for every element in A. Okay, that is the definition. So it is satisfying. And here 1 comma 1 and 2 comma 2, it is also there. Now here in the R3 relation 1 comma 2 is there and 2 comma 1 is also there, but here it is not reflexive because 1 is related to 1, it is not 1 is related to another element too. So this is not a reflexive relation. Okay, so next we will see another relation called symmetric relation. Okay, so symmetric relation. Now again I am taking RB any relation on set A is said to be symmetric relation if A is related to B implies B is related to A, then R is symmetric relation. Okay, that means A is related to B and also B is related to A in our relation, then the relation is symmetric relation. Okay, so here let us see with the example. Here I am taking set A is equals to 5 6 7. Okay, so here we can define A cross A. So here 5 comma 5, of course we will get so many elements, so directly I will give the relations. We can define the relations simply. So I am defining R1 like this. So 5 comma 6, 5 comma 7, 6 comma 5 and 7 comma 5 and 7 comma 6, 6 comma 7. Okay, so 5 comma 6 and 6 comma 5 I have given already, and 5 comma 7 and 7 comma 5 and next 7 comma 6 and 6 comma 7. So here this relation is symmetric relation because A is related to B and B is also related to A, that is also there in R1. So R1 is an example of a symmetric relation. Okay, so here we'll see one more relation on the same set A. Suppose here 5 comma 6 and 6 comma 5. Of course it is also what? Symmetric relation. And if you see another example, 5 comma 6, 6 comma 7 and 6 comma 5, this is another relation, but this relation is not symmetric because 6 comma 7 is there in this, but 7 comma 6 is not there, so that R3 is not symmetric relation. Only R1 and R2 are the symmetric relation on set A. Okay. Now one more relation, right? Now antisymmetric relation. Okay, so here it is important, antisymmetric relation. So again same, I am taking RB any relation and R is said to be antisymmetric relation if A is related to B and B is related to A, then A is equals to B. Okay, if A is related to B and B is also related to A, then A is equals to B. Okay, then the relation is called antisymmetric relation. Okay, so here let us see the example. Here set A is equals to, I am taking 2, 3, 5. Now here R1 I am defining like this. Here 2, 2, 3, 3 and 5, 5. Okay. Next R2 I will define like this, 2, 3, 3, 2 and 3, 5, 5, 3. Next here 2, 5 you can define and you can close. Now if you see this, here R1 is 2, 2 means 2 is related to itself and 3 is related to itself, means 3 is related to 3 and 5 is related to 5. So here the elements A and B are equal. So here the elements are equal. Next here 2, 3 is equal to 3, 2 and 3, 5 and 5, 3 both are there in relation R2, and of course here the first and second coordinates are not equal. Okay, though here 2 is related to 3 and 3 is related to 2, here both A and B are not equal, so hence here R2 is not antisymmetric relation. Here this is only antisymmetric relation. So simply here another example also we can take. Simply x divides y, where x and y which belongs to n. Okay, this is also simple. Here x divides y means here every element, of course, not divides by another number, but every element is divides by itself. So here x divides y and y divides x means obviously we will get what? X is equals to y. Okay, so here this divides here antisymmetric relation. Okay, so this is about antisymmetric relation. Next come to the another definition called asymmetric relation. Asymmetric relation. Now again same, I am taking RB any relation on set A. Okay, and is called asymmetric relation if A is related to B and B is not related to A, then R is called asymmetric relation. Okay, RB any relation on set A is related to B and B is not related to A, then R is called asymmetric relation. So here say, take one example with set A consists of, suppose here 5, 7. Next here I am taking one relation R1 like this, here 5, 7 and 5, 5 and 7, 5 and 7, 7. Okay, and R2 I will define like this, here 5, 7 and 7, 5 and 5, 5. Next here R3 5, 5 5, 7. Okay, so in these three relations, here we can say R1 is not asymmetric relation because 5, 7 is related to 5 is related to 7 and 7 is also related to 5, and 5 is related to 5, and 7 is related to 7. So this is not asymmetric relation. And come to R2, 5 is related to 7, and 7 is related to 5, and 5 is related to 5. This is also not asymmetric relation. But see R3 is asymmetric relation, because 5 is related to 5, okay, but 5 is related to 7, and the 7 is related to 5 is not there. Here 7 is not related to 5, 5 only related to 7. So this R3 is an example for asymmetric relation. Okay. Next we have transitive relation. So now transitive, if of course R be any relation, if A is related to B and B is related to C, then A is related to C. Okay, then R is called transitive relation. Once again, A is related to B and B is related to C, then A is related to C, then R is called the transitive relation. So here you can take some simple example like here 1, 2, 3. Next here I am taking R1 as a relation that is equal to 1, 1 and 1, 2, here 1, 3, and here 1, that already we have taken 1, 2. So now here I am taking 2, 3 and 3, 2, and suppose in R2 I will define like this, here 1, 2, next 2, 1 and 1, 1. Okay, that's all. And here R3 1, 3, 3, 1, 2, 3, 3, 2. Okay. So now if you see the examples, here 1, 1, 2 is there, and here 1, 3 is also there. So 1 is related to 2, and here 2 is related to 3, and 1 is related to 3, means 1, 3 is there. Next, here 3 is related to 2 and 2 is related to 3, and here this 3 is related to 3 does not belongs to R1. Okay, so R1 is not transitive relation. But if you see this R2, 1 is related to 2 is related to 1, so 1 is related to 1, that is there. So R2 is transitive relation. Okay, and come to R3, 1 is related to 3 and 3 is related to 1, but 1 is not related to 1 here in R3. 1, 1 element is not there, so R3 is also not a transitive relation. Okay. Next, equivalence relation. Equivalence relation, this is important. A relation R is said to be equivalence relation, or let R be any relation if R is reflexive and symmetric and transitive, then R is called equivalence relation. Okay, so here equivalence relation means if R is reflexive, symmetric and transitive, then relation R is called equivalence relation. Next we will see one more definition, that is ordered relation. Ordered relation. Here R is transitive, the relation R is transitive but not equivalence, is called ordered relation. Okay, R is transitive but not equivalence relation is called ordered relation. And one more relation here we have that is important, that is called partial order relation. Partial order relation. So if a relation, if R is reflexive and antisymmetric and transitive, is called partially order relation or partial order relation. Okay, so there is only one difference between equivalence relation and also partial order relation. In equivalence relation, reflexive, symmetric and transitive will come. In partial order relation, we have reflexive, antisymmetric and also transitive. Okay, so this is the major difference here, symmetric and also antisymmetric. Okay, so that you have to observe. So that's all about the class. Thank you for watching. Signing off.